Isaac Newton once described time as an absolute stage, a rigid, universal metronome ticking at the exact same rate for everyone, everywhere. He envisioned a steady, uniform rhythm stretching from the edge of the universe down to your very room. However, in October 1971, physicists Joseph Haffel and Richard Keating put that intuition to the test. They took 4 highly precise cesium atomic clocks and boarded commercial airline flights, sending them twice around the world, one set flying east, the other flying west. To measure any deviation, they left a second, completely identical set of atomic clocks perfectly stationary on the ground at the United States Naval Observatory. When the planes landed and the devices were compared, the numbers did not match. The clock flying east had recorded 59 fewer nanoseconds than the ground reference, while the clock flying west had recorded 273 more. This discrepancy was thoroughly verified and not caused by mechanical failure, aircraft vibrations, or atmospheric conditions. The clocks operated exactly as designed. The devices didn't break. The actual flow of time experienced by the clocks was altered by the velocity of the aircraft. Physical measurement confirms that time stretches when objects move. The question is why? To see how movement manipulates time, we can build a hypothetical device, a light clock. It consists of 2 parallel mirrors with a single photon bouncing between them. Every time the photon completes one vertical trip between the stationary mirrors, we count 1 tick. Now place that identical clock onto a spacecraft moving laterally at high speed while you observe it from a stationary position outside. The photon continues bouncing up and down, but because the mirrors are moving sideways, the light must travel along a diagonal zigzag to reach the opposite surface. Physics demands one absolute rule: the speed of light is completely constant. A photon cannot accelerate or decelerate to compensate for the situation. By looking at the Pythagorean theorem, the geometry creates a trap. The diagonal path the light now takes is mathematically longer than the straight vertical drop it took when stationary. If the photon must cover a longer distance but is strictly forbidden from increasing its speed, the journey simply must take more time to complete. From a stationary perspective, a moving clock literally ticks slower. Movement mathematically forces time to stretch, preserving the constant speed of light. This concept is tracked by the Lorentz factor, which defines how much time stretches based on velocity. At standard speeds, the effect is negligible, but as an object approaches the speed of light, the curve spikes violently upward toward infinity, and time nearly stops. This curve dictates the daily operation of the global positioning system. The network relies on 31 satellites orbiting Earth at roughly 14,000 kilometers per hour. Due to these high orbital speeds, special relativity demands their onboard atomic clocks run 7 microseconds slower every day compared to receivers on the surface. GPS calculates position by timing light speed signals down to the nanosecond. Uncorrected, these relativistic errors multiply quickly, creating a navigational drift of over 11 kilometers every day. Relativity is an active engineering requirement. Without programming satellites to compensate for time dilation, modern digital navigation would be completely useless. When high-energy cosmic rays strike our atmosphere at an altitude of 15 kilometers, the impact shatters them, creating a shower of subatomic particles called muons. Muons are highly unstable. When at rest, they spontaneously decay in approximately 2.2 microseconds. That is far too short a lifespan to cross 15 kilometers of Earth's atmosphere and hit the ground. Yet ground detectors record massive quantities of muons arriving constantly. This happens because the particles are traveling at 99.8% the speed of light. From the ground, the muons' extreme velocities stretch their lifespan from 2.2 to nearly 35 microseconds, providing ample time to hit the surface. But from the muons' perspective, their lifespan remains 2.2 microseconds, and the 15 kilometers of space physically contracts to just 950 meters. Time dilation from the ground and length contraction from the particle arrive at the same physical reality. The math holds, and the muons reach the dirt. The rigid, universal metronome of Newtonian physics does not exist. Space and time form a fabric that bends and stretches asynchronously depending on who is moving through it. Albert Einstein proved that time is a participant, not a fixed stage. There is no universal present moment shared by the cosmos. My now and your now can be physically different moments if we are moving at different speeds. We are biologically blind to this because we move too slowly. At the 900 kilometers per hour cruising speed of a passenger jet, time diverges by only a few imperceptible billionths of a second. Furthermore, time dilation is an entirely relative phenomenon. Even if you were traveling at 90% the speed of light, your heartbeat, your thoughts, and the watch on your wrist would feel completely normal to you. The reality of relativity only reveals itself when you compare your clock against one held by a stationary observer. Both measurements are entirely valid within their own frame of reference. Velocity irreversibly warps the fabric of time and space, pulling apart our assumption of a shared reality. But speed isn't the only force capable of doing this. Mass and gravity also bend this newly discovered spacetime.